Hello guys, in this particular video, we will discuss the mean value theorem. Welcome back to Self-Help Maths Academy. So let's begin with our discussion. So what is this Rolle's theorem is all about? How we prove this Rolle's theorem is our discussion. So here, the Rolle's theorem says that suppose that y is equal to f of x is continuous at every point of the closed interval AB. So there is a function f of x, y is equal to f of x, which is defined in the domain, say D, if I take this closed interval AB. So this is the domain of the function. And they say that this particular function is continuous in the closed interval AB. So let's understand what is this continuous. Continuous means there is no break in the interval. Between A to B, there is no break in the function. It's a smooth curve, you can see. So there is a continuity between the interval, closed interval A and B. And it is differentiable. The given curve is differentiable at every point of its interior open interval AB. So here it is closed interval. This given function is continuous. It is continuous and it is differentiable. It is differentiable where? In the open interval AB. So why we are not taken the end point? Because differentiable means what? It is the tangent drawn to the curve, you can see. So if I take the edge points, I mean like the last end points if we take, then you'll be getting the sharp points. So if you get a sharp point, say for example, if you see the curve, if you see the graph for the mod x function, like this it comes, okay? So mod x function, this is your mod x function, where you can see the graph of the mod x function when you observe carefully. So you'll be getting a sharp point at x equal to 0. So this is continuous. You can observe there is no break in the graph. So modulus of x will be continuous, but it is not differentiable at x equal to 0 because it is having a sharp point here. You can see the curve, and there is no tangent. There is no tangent which is at x equal to 0. In other words, the same way here it is differentiable within this open interval AB. Everywhere it is differentiable except at A and B. So these are called as sharp edges or the sharp points. Okay, so these two are the given data, and also they have given that the given function is equal at the end points. F of A will be equal to F of B. So these are the given things in the Rolle's theorem. One is the given function is continuous and it is differentiable in the open interval AB, and also F of A is equal to F of B. So clearly you can see from these graphs. So here the function at A, it is F of A, and the function at B, it is F of B. So here F of A is equal to F of B. Here also you can observe this is a curve, and here it is f at the point of A, f at the point of B. So both the values are equal. So this is given. If this is happening, if these all things are happening, then there is at least one number C. So there is one number in between this interval AB. There is one number C such that if I take my derivative at that point C, it is equal to 0. It is equal to 0. Okay, so this is the the theoretical meaning. So let's understand what is geometrical it is trying to say, the Rolle's theorem. So if I take the graphical meaning of it, you can see here that I have drawn two graphs. So first graph, if you observe, this is our function y is equal to f of x. So here you can see that we have a function y is equal to f of x. Let me change the color here. So you can see this is our function here. Okay, so okay, so I will take this point as say A, this point as say B, and this is our y-axis and this is our x-axis, and it is our 0. And what I do now, I'll be taking a point C. This is our function y equal to f of x. Okay, So let us take one point C in between this, such that if I draw the tangent at this point, this is our tangent is nothing but what? The derivative. That is derivative at that point. It is equal to 0. So that you can clearly see this tangent is parallel to, here if I draw one more line, this you can see this tangent is parallel to the horizontal, this horizontal tangent is parallel to this line, or the parallel to the lines which crosses the function y equal to f of x horizontally. Correct? So that means it is not making any angle with the x-axis. In other words, so there is no angle, this tangent is not making any angle with x-axis. When there is no angle, that is x equal to 0, that implies the tan theta, the tan of angle is 0. So therefore, the value of the derivative is equal to 0. So this is the geometrical meaning of the Rolle's theorem. And here you can clearly see your f of a is equal to f of b. But is it that only one point we will be getting in between a, b? So in order to understand it better, I've shown you one more graph. Here you can see in another graph, you are getting such points. Like see here I've got C1. So let me take this as C1 point. Here there is a point C1 and this is a point C2 and this is a point C3, which are lying in between A and B. If you take a tangent at this point, that is f dash of C1 is 0. At this point, you take f dash of C2 is equal to 0. At this point, f dash of C3 equal to 0. So this implies at least one point exists, at least one number C exists in between AB. So there may be more also. So from figure 1, it is clear that there exists one point. And from figure, it is clear that there may be many. There may be many such points in between the open interval AB, such that the tangent at that point is equal to 0. Okay. So this is how, guys, we're supposed to understand the geometrical interpretation of the Rolle's theorem. Okay. So here, in order to prove this, we need some more theorems like extremum value theorem. We need the first derivative theorem, and we need the intermediate value theorem. So let's understand now how to prove this. So for that, we need the first derivative theorem, and moreover, the first derivative before first derivative theorem, the extremum value theorem says that if suppose you are having a function f of x, if you have there is a function f of x which you define in the closed interval a. So here you can see what I said. If y is equal to f of x, if it is continuous function in the closed interval AB, then it has both absolute maximum, and it has absolute minimum. Okay, so this is the extreme value theorem. So clearly the given function is continuous on the closed interval AB, so we can apply the extremum value theorem. So this is the extremum value theorem, guys. So now we have the first derivative theorem, which says if f has the local maximum or minimum value at an interior point of C of its domain. So here clearly they're saying that if f is a function which is having local maximum and local minimum value in its interior point. So here you can clearly see, if I take the interior point on the open interval, say that is AB here, then there is a point, say C, such that if I take f dash at this particular point, the value will be equal to 0. Okay. So these are the two important theorems which I want to utilize in order to solve this Rolle's theorem. So let's begin with the proof of this. So here, clearly we can see that given, we will consider what is given. So by the hypothesis, it is given that f of x, y is equal to f of x, it is continuous. It is continuous where? In the closed interval AB. Okay. And yeah, if suppose it is continuous, by using the extremum value theorem, what it says? It says that the given function will attain the absolute maximum and absolute minimum. So it takes the absolute maximum and absolute minimum. It attains the absolute minimum. Okay. So in the closed interval AB. Okay. So this is known by using the extremum value theorem. So this can occur. This absolute maximum and absolute minimum can occur. This can occur, or this is possible only when there are three conditions. So what are the three conditions? First one is, it is possible at interior points where f dash has to be 0, Second one is, it says the first point is your derivative. The first derivative f dash has to be equal to 0 in the interior point of bits, that is in the open interval. And the second point is, at interior points means in the open interval, at interior points where f dash does not exist. So where f dash does not exist. So according to the conditions for the critical points, when you see the critical point, a critical point is the one where you can see the derivative, the absolute maximum and absolute minimum exist only when f dash has to be equal to 0 or f dash does not exist. So that particular point we call it as a critical point. So if you take that particular concept here, so here clearly we can say that this absolute maximum and absolute minimum is possible only when f has a derivative which is equal to 0 in the interior point or in the open interval, in other words you can say, and at an interior point, that is in the open interval AB, f dash does not exist. And third point is at the end points. It is possible at the end points. Okay. So in the end points, that is A and B, we can say that the absolute maximum and absolute minimum occurs. So now let's see what are the possibilities out of 1, 2, 3. So with the help of our hypothesis means the given data of the particular theorem. So it says that f is continuous. It is continuous in the closed interval AB, and f is differentiable. It is differentiable in the open interval AB. So when it says that it is differentiable in the open interval AB, means f dash exists, the derivative exists. So by this particular hypothesis, clearly we can eliminate the second one, that is the f dash does not exist. So according to our hypothesis, it exists. So therefore we can clearly eliminate the second part. So now we are left with the first part and the third part. That is, first part is at an interior point where f dash is 0, or it may be at the end points in the closed interval AB. So let's start with the two things now. So we will understand which among them will be true. If both are true, then how we will prove it. So what is this? The first part is either the maximum or the minimum value occurs at a point C between A and B. So first point is what? F dash has to be equal to 0. F dash has to be equal to 0 in the open interval AB. So how do we prove this? The first derivative theorem says that, just now I explained, the first derivative theorem, it says that this given function, if f of x is equal to, if it is a continuous function, then what we have, if there exists an open interval AB and there is a point C in between this open interval AB, then f dash at the point of C will be equal to 0. That's what we have discussed here. You can see the first derivative theorem says that if f has the local maximum value or the minimum value at an interior point, that is an open interval AB, so then f dash, if we define at that point, it is equal to 0. So clearly guys, we can see that either we are assuming that both absolute maximum and minimum is achieving, so it occurs, then there is a point C such that where in the open interval AB such that f dash is equal to 0. It's a direct proof by using the first derivative theorem. And we found the, this is one of the point which we wanted. So f dash of c equal to 0 means that is a proof of the Rolle's theorem. It is in the first case. What about in the third case? Third case says that it is a local absolute maximum and absolute minimum occurs in the end point of it. So let's see how exactly we will prove this also. Now, if both absolute maximum and absolute minimum, this occurs at the end points, if it is occurring in the end points, then also they have given that the Rolle's theorem, given that the condition is f of a equal to f of b. This is also one of the condition. If f of a is equal to f of b, then you can clearly see f of a equal to f of b means what? It is something like, say, your function f of x is equal to f of a, which is equal to f of b, means it is a constant function. So clearly, if I take, say, for example, f of x is equal to c, then if I take x is equal to 1, it is f of 1 is equal to c. If I take x is equal to 2, f of 2 is equal to c. So on, you take any value for x, that value will be what? It's a constant value. Similarly, since f of a is equal to f of b means, in this case, a function must be a constant function where within the interval where x belongs to the closed interval ab. So in each interval, you take any x in between this closed interval ab, your function f of x will be equal to f of a, which is equal to f of b. Means it's a constant function. If you take a constant function, guys, then if suppose it is your constant function, say k, take a derivative of this function f dash of x, which is equal to 0. So derivative of the constant function is 0. So in particularly in place of x, if I take is equal to c, it is nothing but what? F dash of c will be equal to 0. So this is true again in the open interval ab. So thus what thus what we say. Therefore in the third case also, our the Rolle's theorem is possible. The Rolle's theorem is proved, you can say. So this is how, guys, you're supposed to prove the Rolle's theorem. I'll give you one important note with respect to this Rolle's theorem. Whatever the hypothesis in the Rolle's theorem we are studied, they are very, very essential. If at least one point fails, even at a single point, then we will not get the horizontal tangent, or you can say that the Rolle's theorem fails. So what are the essential points in the Rolle's theorem? The given function f of x has to be continuous. It has to be continuous in the closed interval ab, and it has to be differentiable. It has to be differentiable in the open interval ab, and f of a is equal to f of b. These are the three important conditions, or we can say the hypothesis, which are essential. If this happens, then only there exists a point c belongs to the open interval ab, such that your f dash of c is equal to 0. This happens. So this is the output of the Rolle's theorem. But these are the three important essential conditions, or you can say the hypothesis of the Rolle's theorem. So let's see if at least one fails, how the graph fails, or how the Rolle's theorem fails. So that I'll explain with the help of graph. You can observe this particular graph. So here, in this particular graph, y is equal to f of x is noted, and here this y is equal to f of x is discontinuous at an end point. You can see clearly at an end point, this given function at a, it is not continuous. So it is defined within the closed interval ab, but it is not continuous at a point a. It is discontinuous at a point a. But as per our Rolle's theorem, it says that it has to be continuous in the closed interval ab. So at least one particular point fails, then I will not get a horizontal tangent. I can't draw a horizontal tangent here. So thus, in this case, Rolle's theorem fails. Now come to the second point, where you can see in this curve, you are having the continuous function. Here you can see the continuity here. Actually, it is between a and b. Continuity fails. It is discontinuous in the interior of the closed interval ab. somewhere at the point x naught, the given function is not continuous. There is a break you can observe in the curve. So this again says that the given function fails at continuity. So again, we will not get a horizontal curve in this case also. So again, you can see the third one where the given function is continuous. The given function is continuous, but it is having a sharp point. You can see the sharp point. So sharp points means we will not get a tangent. In other words, the given function is not differentiable. It is not differentiable in the interior of AB. Interior means at x naught you can see. At x naught, the given function is not differentiable because of the sharp curve. Okay. So in these three cases, either it is one of the condition at least one point. You can see clearly only at one point it is not continuous. Here it is not continuous only at one point. Here it is not differentiable only at one point. Even at one point, the hypothesis fail. Then we will not get the horizontal theorem, horizontal tangent. So this, you can see that there may be no horizontal tangent if the hypothesis of the Rolle's theorem do not hold. So that is the essentiality of the hypothesis of Rolle's theorem. So this is how, guys, you should understand geometrical meaning of Rolle's theorem, theoretical meaning of Rolle's theorem, and you can prove it easily. So today we have proved the Rolle's theorem. Hope you like the video, guys. If you like the video, please subscribe the channel and forward to other students so that it can reach to maximum students. In the next video, we'll come up with the mean value theorem. Thank you so much, guys. Please take care. See you in the next video.